I think by the middle of the century, I'm very, very confident that most fossil fuel use will go away. We're going to all drive electric vehicles. We're probably going to fly on some electric planes, not for long distances, but for regional planes. Urban air mobility will become a reality.
The electric vertical takeoff and landing machines, I've been working on some of those. It's pretty fun stuff.
Yeah, they need better batteries, right? That's like the key limiter. But they're a lot more redundant than helicopters. They can be a lot safer. So I think we'll get around differently. We'll have abundant, cheap, clean energy. And when you have that, you can invest that in sort of solving whatever problem you want, right? If energy doesn't have this negative externality, I don't know what creative entrepreneurs are going to figure out to do with cheap, clean energy, but I bet the world will be a better place.
Welcome to the American Optimist. We have Gene Berdichevsky here, the CEO of Sila. Gene, thanks for joining us today.
Great to be here. Thanks, Joe.
You guys have raised over $1 billion into this battery area. You were the 7th employee at Tesla, is that right?
That's
7.
Right. Yep.
And you hold a bachelor's and master's in engineering from Stanford, which I went to as well. What year did you get out of Stanford?
I left in 2004.
Similar to me. That's when I was there. We didn't know each other.
No.
I was too busy in the computer labs. And what kind of engineering were you studying?
Yeah, I was a mechanical engineer, and I was probably too busy at the solar car shed.
The solar car shed. That's cool. And so you're the 7th employee at Tesla, and let's go back a little bit before that. Your family came to the U.S. from Ukraine, I believe, right? So that must be a little bit of a difficult time for you with seeing what's going on there. Do you have friends there still?
Yeah, I was born in Ukraine. I mostly grew up in Russia. So we came from Russia to Richmond, Virginia, in '92. I was pretty young. It's certainly difficult seeing what's going on. Fortunate that most of our friends and family have been long gone, but certainly still a lot of ties to the area. And actually, my last name stems from a Ukrainian town of Berdichev, so a lot of roots back to that area as well.
And what brought your family to the U.S.?
Opportunity. My folks were electrical engineers working on nuclear subs in Russia.
Oh, wow.
And they saw the opportunity America had. We have some Jewish roots as well. It wasn't sort of the most welcome place for Jews in Russia, and so that when they had a chance, they came. And my dad's an entrepreneur, and he's built businesses here and the like since then.
Awesome. And at Stanford, you were really into solar cars, and I guess did you drop out of Stanford ultimately for your master's degree?
Technically I did. I dropped out kind of with a couple classes to go after my third year. Joined Tesla. Saw the opportunity. Saw sort of the opportunity to take what we'd done at Solar Car and really take it to kind of.
Was Elon there yet when you joined?
Mostly no. So I spent a lot of time with JB. I mean, Elon was already an investor. He was on the board. But day to day, we worked out of JB's living room. That was the Tesla Annex back
That's
then.
Cool.
And a couple shops in Menlo Park and in San Carlos.
And you were working on, I guess the first car was the Roadster. So you were working on the Roadster battery at the time then?
Yeah, when I showed up, there was nothing. There was a 2-room office, and the 3 new technologies were really the motor, the controller, and the battery. And the motor's 100 years old, invented by Nikola Tesla himself. The controller was about 20-year-old technology, and the battery we were super gluing things together. So I said that seems like the nascent one.
I was just at the factory in Austin last week. And for some of us, they gave us like a tour. They were showing how they make the batteries there, and there's like a million these little wires, and someone actually does it partially by hand, which is very unintuitive to me. They said they have machines, but they also have people who are faster at some part of it. But you guys had to make machines that created these things, though.
Yeah, so I suspect they're still using the wire bonding process. That was sort of a way to make these electrical connections to the batteries with what would be also kind of a fusible link, so it's sort of a half safety, half performance. But I'm surprised to hear that there's humans.
They told me there's some parts by hand that are more efficient, which I didn't believe either. But who knows? That's what they're saying. But it looks like they're making their own motors and they're proud of it. So there's some advancement there too, I guess. But the battery's the bigger part of the advancement.
For sure. I mean, compared to where it started, right? A motor that we started with was probably close to low 90s% efficiency, and now they're probably I don't know the exact details, but they're probably upper 90s on the efficiency of the motor. So those are big gains, but those are relatively sort of modest compared to taking batteries that are incredibly inefficient and expensive and what they've achieved now.
So what was it like working on like this is the first massive lithium-ion mass produce batteries for automobiles? Like you guys, like what do you have to do to achieve that?
So there's a ton of skepticism, right? The auto industry basically looked at it and said, look, you can't use laptop batteries to make cars. That's just dumb. It's never going to work. It's unsafe. You got 7,000 of them. All those connections are going to fail. So there's a huge amount of skepticism that we heard all around, but it was sort of one problem at a time. And you don't know, as a young engineer, you don't know any better that something's not supposed to be doable, and you just figure it out. So the key issues were, how do you connect 7,000 cells together? The wire bonding you saw was a big part of
7,000
it.
cells in the initial Roadster battery.
Yep. 99 groups in series, 69 in parallel. So that was a big challenge. The other big challenge was really safety. So batteries can develop defects. They can go into thermal runaway. And one of the big things we solved is that if that happens, in one battery, that it not propagate to the rest.
So all 69
exactly. So if one happens to have a defect that causes a failure, if it propagates, you have a problem, and if it doesn't, you have an inherently safe system. And so we were able to make an inherently safe system, a lot of thermal challenges in order to make that work.
Was Elon involved in choosing 69 as the number of the Roadster batteries?
No, that was me. That was me.
I'm just sorry. We can edit that out. Maybe we'll see. So you're at Tesla, one of the most exciting companies in the world. Why did you decide to step down and finish your master's degree and start Sila?
It was really a choice between, after shipping the Roadster, doing the Model S, which I knew was going to be a 5-year project and was going to be incredibly hard and incredibly fun, and kind of going back to the beginning. And I wanted to take everything I had learned, seeing this company go from 7 people to 300, from no product to a product in the market, and really apply it to another part of the energy puzzle. And so with that in mind, I left and went and spent a couple of years studying the science of energy, which led me to batteries, which led me to the chemistry side of things, and ultimately got exactly what I wanted, which is to start a company that has a chance of making a huge impact on the world.
I'm a computer scientist. I'm always a small investor, proud investor in your company, but I'm not an expert in batteries. Take us through the basic chemistry of a battery. What are the factors that limit storage and density, and how do you overcome these factors?
Yeah, so a lithium-ion battery in particular is a fairly mechanical and intuitive system in some respects. So there's 4 components that matter. I promise I won't go too deep, but there's the anode, which stores the lithium when the battery's charged, and the cathode that stores the lithium when the battery's discharged. Think of those as like housing materials for the energy carrier. Those are the 2 things, if you remember nothing else, those are the 2 materials that really matter.
And the anode and the cathode, and they store the lithium.
And they store the lithium. One when it's charged, the other when it's discharged. And
how's the energy being stored? It's a lithium-ion battery. What does that mean?
So that means the lithium atom is the energy carrier, and it's physically residing in the anode when the battery's charged. It's forming bonds with, in conventional batteries, the anode is graphite, and our batteries, the anode is silicon. Mm-hmm. And the energy is stored in those chemical bonds. And then as you discharge the battery, the lithium moves to the cathode, which in conventional batteries is metal oxide. And it ends up bonding with that metal oxide.
And just to go a little bit deeper, just for people who are interested, like what are the bonds that are storing the energy? Is it like lithium, and it's not interacting with the silicon, or is it, or what's going on there?
So in conventional batteries, it's the atomic structures, essentially 6 carbon atoms and 1 lithium atom sitting in the middle. And so it's LiC6 is the chemical, kind of how it compounds. And then in the cathode, it's a metal oxide. In your phone, it's a lithium cobalt oxide. So Li, cobalt, CO, oxygen, O2. And so that's a crystal structure. And again, the lithium atom kind of sits in the middle or in some part of that crystal lattice. And so those are relatively kind of weak bonds, and it stores a sort of a nominal amount of energy.
When you're charging it, it's moving the lithium to the C6 away from the COO2.
Yeah, exactly. And then as you close the circuit and you let the electrons run the other way, it wants to go back the other way.
The lithiums want to go back to the cobalt. And what happens when the lithium's not there? What's the cobalt and the O2 doing? Like, is it just cobalt and then?
It's basically hanging out. It's an empty home.
Is the oxygen still there, or is it pulled in from the air, or just
oxygen's still there? It's a solid material, right? So it really, like, the best analogy, and we get into some of this in still an accessible way in a white paper we have on our website, where the analogy we use there is think of 2 auditoriums, right? Mm-hmm. And the lithium cobalt oxide, or the main nickel oxide or whatever you're using in the cathode, that's one auditorium full of seats, and the carbon or silicon is an auditorium full of seats.
And the anode that you have that has more silicon in it, what's the chemical there then?
So there, the 4 atoms of lithium actually bond with a single atom of silicon. So you remember with carbon it's 6-to-1. Here it's 1-to-4. So it's 24x atomically better. And this is sort of the real advantage of the chemistry we work on. At the atomic level, it's that much more efficient. Now silicon's heavier, so it's only about 10 times better on a weight basis. And then the other thing that happens is the silicon expands about 3x as you charge it with lithium. And so on a volume basis, it's about 3 times better, right?
Got it. So but your battery expands more then.
So the key is how do you make that expansion manageable with every charge and discharge? And so
you don't want to blow up the phone or
the
car.
Exactly. So that's, we spent a decade. We were the first to kind of crack the code on this in a way that's scalable, and we can replace the entire.
Is there a trick you can explain, or is that the secret IP?
No, conceptually it's we created a superstructure that allows the silicon lithium to expand and contract inside of a larger scaffold particle, right? So it's sort of a, think like raisin bread, and it's like the raisins are expanding and contracting, but it has kind of an outer rind that keeps it all intact.
Got it. So because it's 24 times more dense, if you could still have a little bit more extra room, it's still much more dense than the other one.
Exactly. Because it has so much, it's so much better in theory, right? Even in a practical implementation, it's still a lot better.
So right now, the high-end lifespan of a Tesla battery understands about 500,000 miles, 500,000 miles. Does it need to get to 1 million or 2 million miles? Is that possible? Is it important, or is it right now it already lasts so long the car's going to break down anyway?
Look, I spent a lot of time thinking about the long arc of transportation and how do we get to every single car in the world being electric. And what we need to do is bring down the cost of energy storage to do that. But there's actually sort of 2 ways to reduce the cost. One is you can bring down the upfront cost. The other is you can increase the residual value, right? And so as you move to batteries that are able to last 1 million, 2 million, 10 million miles, the residual value is basically the same as the upfront value. And the cost of capital on an auto loan is very, very low.
So you just keep the batteries, put them in a new car eventually? Eventually,
that's where we're going to be. In the meantime, you're going to recycle them, but the less often you have to recycle them, the kind of the less new cost comes in.
And tell us, for batteries in the world, I have batteries in my phone and on my laptop and in my car.
On your wrist, in your AirPods.
On my wrist, I have an old-fashioned watch on, but it's true. Most people nowadays who are normal have Apple watches, which is there. And so, how much batteries are used? How much battery material is used for all the wrists and phone and laptop versus cars? What's the amounts?
So there's about 10,000 phone batteries worth of material in a single car.
Wow, a single car, 10,000 phones. So for the battery market, the cars are just way more stuff.
Completely dominant.
So you're just focused. If you're running a company, the cars is the thing to focus on.
The value in a phone or a consumer device is still quite high. And when you're running a company, you can first produce a certain quantity of material, and then you can produce 10x.
So you guys went into wearables first because you just produced enough material for them.
Exactly.
Are you going to go into phones at some point? It seems like a smart thing to do because they're valuable.
It's basically going to go wearables, phones, cars, the grid, right? It's sort of as we get more scale.
And the grid is the one thing you could potentially use more than cars, because in order for solar and wind to actually be something that actually works for our civilization, we need a ton more storage, right?
It's about the same as cars, so it's more like a 2x.
Well, it is right now, but if you think about
No, it will be.
It will be.
Yeah. Today cars are 10.
Today cars are way bigger.
10 or 20 times more.
That's really interesting, because my intuition is that we just need a ton more storage before renewables can actually. Right now, renewables to me aren't actually that useful yet, because if it's just the wind's not blowing, you still need to turn on the coal plant,
right?
So or whatever, but eventually you're gonna have enough batteries that you can't just have renewables and store and charge stuff. But you're saying that's gonna be about equal to the amount of batteries you need for cars. When we get to that point.
It'll be much higher utilization in the grid, right? So if you think about the energy stored in your EV, you're not using all of it every day. Although that will also change. So the other answer to your question of kind of why do we need a 1 million mile battery or 10 million mile battery is, as we get to autonomy, which obviously is going to take a little longer than everybody expected, vehicles are going to go from driving 100,000 miles in 10 years to driving 1 million or 2 million miles.
The vehicle should always be on for everyone. It's shared economy. It's just going. Yeah.
And as you can imagine, with the cost of recharging an EV being almost nothing compared to the cost of refueling a car, autonomous EVs are going to be not just a little cheaper than gas-powered EVs, but they're going to be an order of magnitude cheaper.
That's
They're
great.
Just 10x better.
Eventually, we're going to have all these tunnels under our cities with autonomous vehicles going back and forth forever, and you don't want to run out of battery.
Exactly. I look forward to that day. They'll need a lot of battery materials.
We're pushing Elon and Austin to trying to get that forward. So, but that's really interesting. So it's the car market and the grid long term are pretty similar. They're the two things that matter.
Yeah.
And
that's the mission of the company too, right? We love making products like Whoop better. We want to make your phone better, but we're really here to
because you could make the phone battery last way longer.
Yeah, exactly, and we will. That's all gonna.
My phone may be able to last for like a few days or something if you get this right, or
you can probably extend the runtime of the cell with not just our technology but other technologies by roughly a factor of 2. That's kind of what's out.
Well, right now it lasts for a little over a day. So
yeah, you can get there.
You're saying so that the mission of the company though is not just about making your phone last twice as long. It's actually enabling a future where the renewables can work on the grid and where the autonomous vehicles can go forever.
Yeah, exactly. And that future will be a lot less extractive of resources from the earth. Well, as a matter of fact, once all of the sort of nickel and cobalt and copper and aluminum is in the batteries in the world, like it'll all end up being recycled. Basically 100% of lead acid batteries are recycled today. So you can imagine you sort of need to seed all of that.
You have like a
minerals.
one-time mining thing where we're going to mine like crazy for a couple of decades, but then we're just going to recycle it all and reuse it.
That's
the way
the
it's
vision. That's how it should work. And that's how it works with lead acid batteries today. They're all recycled. And so it's like these materials are too valuable to not be recycled. And so you can kind of think of it this way: for the last 100 and some years, almost all of the energy that humans have used has come stored in the chemical bonds of fossil fuels, and those are effectively single-use batteries.
My dad likes to call them hydrocarbons.
Yeah. They're it takes about 100 million years to recharge them, right? And so with batteries, you're going to have chemical bonds that are useful for 1,000 times, 10,000 times. So even if they're 10x more expensive, it doesn't matter. The economics.
If you could make
better.
Hydrocarbons efficiently, would there still be some use cases where you might want to use them?
Yes. I think flight is going to be something that's going to be very, very hard to.
It seems like for jet planes, to just like maybe make jet fuel and
that's right.
Take it out of the air or something.
Yeah.
But for cars, for phones, for everything, for grid, it's all batteries.
Yeah. Why waste a bunch of inefficiency going from electrons, which we're going to get from the sun or the wind or fusion or wherever? Why take it through a convoluted pathway to make a chemical bond only to kind of bring it back to probably electricity in the end, anyways?
No, of course. The price of lithium, speaking of mining, has gone up like 500% or so in the last year, I think. So what effects is that having on the electric vehicle market, on what you do?
Not a lot of effect on what we do.
Is lithium a small part of the cost?
It's a very small part of the cost, but anything that even if you take something that's 2 or 3% of the cost and 5x it, now it starts to become really meaningful.
10 or 15% more. Yeah.
So we saw battery prices increase for the first time, and probably in 30 years. This past year, and
I guess everything's going up in price right now.
But in particular through supply shortages, right? So this is and really, sorry, not even supply shortages, but really demand far outstripping, right? There's so much demand.
So
for
much
EVs.
new demand for these for EVs, for lithium, for cobalt, I guess, and other pieces.
Yeah, and cobalt, for example, cobalt is a co-product of mining. It means you don't find a primary cobalt mine, you find a nickel mine that has some cobalt.
You get some extra cobalt.
And so, the amount of it produced is very, very inelastic. And so you have a real challenge with things like that. Nickel, is used for, primarily nickel is mined for steel production.
And I understand Russia has a lot of the nickel. Is that a problem right now?
That will be. If I haven't followed what the sanctions are like around the nickel, but that could certainly pose a problem. But it's used for steel, and steel is sort of has a very inelastic demand as well. Yeah. Like you need the steel you're going to need, even if it costs a bit more. Whereas if you can, so EVs are kind of right now getting a little bit of the short end of the stick of supply.
And I mean, how's this going to evolve? Let's say we have to all of a sudden put the grid to work for renewables or whatever like that. Like, is that going to shoot up the cost for a while of these things? Like, could all this stuff be really expensive for the next couple decades?
I don't think it's going to be a couple decades. I think we're talking about years. And I think this is very natural for an industry that's going from kind of 1% penetration to 10% penetration. It's really, really hard to go from, 10x the scale of an industry over the course of 5 or 7 years. Once you're at 10% going to 20 or 30, that's a lot easier. That's a lot more predictable. Right now,
so we're kind of this really big jump right now, but then we'll start to be predictable and be able to plan ahead.
Right. Exactly. Because it's not going to go exponential forever. We're going through this exponential at scales that no one's really dealt with.
It's a big market, though. I mean, what percent right now are electric vehicles?
I think 2-3%, something like that.
So that could jump up 10x in the next
right. And so getting
decade.
to 30% is going to be absolutely, and that
So
getting
it's
to
going
30% is
to
going
be
to be really
crazy
hard.
5 or 10 years.
Crazy 5 or 10 years, but from 30 to 60, that's only a 2x jump. That's same scale, but only a 2x jump.
And so for you guys, you're obviously positioned very well. Everyone needs what you're doing. Like, you're just trying to ramp as fast as you can and making big partnerships. Like how are you thinking about this?
We are. We'll have some announcements coming on scale, but that's the name of the game now. The same technology that we ship in the Whoop today, which is the first product with our first product in the market with our technology, and really the first product with any next generation battery technology in the market. That same material, that same technology is what we're going to ship in the first cars. And so it's really about taking it several orders of magnitude. Starting from lab scale, we've over the last 7 years, we've scaled up about 10,000x from lab scale to production scale. From where we are today to supplying all cars globally, is going to be probably another 5 orders of magnitude.
That's a lot.
Yeah. And it's not just, spinning up AWS servers, right?
You can't just turn it on, yeah.
We will build...
You're making fun of me as a computer scientist, huh?
we'll probably...
You can't just press a button like you assholes.
We'll probably have to put tens of billions of dollars of capital on the ground to meet the demand just for our component, just for the anode component, and the whole industry as a whole is putting hundreds of billions of dollars. I mean, one to kind of come back to this sense of scale. We're talking about cars and phones. When Tesla built the first gigafactory, it was bigger than all of the demand for all consumer electronics at the time. Right.
Wow. That's huge. I mean, it is just a huge, and it's just such a big amount. And like one of the things that one of Elon's my friends was like one of Elon's right hands was telling me is he thinks the batteries at scale, you might just use something much cheaper, like an iron-based thing, because it's just so cheap. If you need, she needs something cheap at scale. Like, how do you think about that? Like what does this look like at scale?
So remember, we talked a lot about the cobalt oxide, right?
Yeah.
So there's a different cathode chemistry called iron phosphate, and it's iron-based. It doesn't have nickel, doesn't have cobalt. It's lower performance, so you can only get a 200-mile range.
You wouldn't want to use it on a car, but maybe for the grid or something. If you're just trying to get the grid to have enough batteries.
There are that's right. Although I being somebody who's in lithium-ion, I actually think the scale of automotive will also lead lithium-ion to dominate most of the grid. There will be parts of the grid.
It's just going to get so good because of automotive needs that you might as well just use the good stuff you're already making anyway. That's right. It's just going to be cheaper.
That's right. It tends to be that the thing that gets hundreds of billions of dollars of investment over the course of decades is also really competitive in adjacent markets, and that's such an adjacent market.
No, that makes a lot of sense. So the lithium-ion is the biggest focus, and so you started with Whoop. And you have joint battery ventures that are public with BMW and Daimler. I understand.
They're two of our flagship auto partners.
How did you close the deals with those guys? Like, what did that look like, and why are they working with you?
That was tough. All of this was sort of before the world really. I think the world really changed in 2020. The kind of, I would say, the global pools of money recognized that kind of EVs are here to stay, and this isn't a fad.
People weren't really sure of that before.
It took till 2020. I mean, It was reflected in Tesla's stock price, but that's sort of a reflection of what's happening behind the scenes. And at that point, sort of all the car companies had were becoming fully committed to electrifying their fleets. Some are still sort of holding out, dragging their heels, but I mean, it's game over.
Everyone wasn't sure if it was real. People thought maybe this is like a woke green thing that you're supposed to say, but then it actually turned out to be true. That it just seems just like a better way to do cars.
Yeah, and they're just better cars, right? That's the key. And that it's not just green. It's not green. They're just better cars.
I was driving. I had a Tesla for a while, the S model, and I had an old 3 Series BMW that I used to drive a lot, and I was driving it a few years ago, and I hadn't driven it for a year, and I thought maybe it was broken, and then so I took it into the shop, and it turned out it was just so much worse than the Tesla that it wasn't actually broken. So I really do appreciate the better electric cars.
And so there were champions at companies like Mercedes and BMW that believed in us before kind of the whole world shifted, and now we're going to help them electrify and make much better
electric
EVs,
cars.
right?
Yeah.
Our chemistry. It lives at sort of this fundamental layer, and our goal is to support all EV makers, right? So our hope is that every car maker will use Sila technology, but those will hopefully be some of the first.
That's awesome. And you've said before the 20th century was built on the science of combustion, and the 21st century is going to be built around battery storage. Like what does that look like more broadly in life? How will our life be different because of this?
I think fundamentally the world's going to be much, much cleaner. And we may experience that directly. We may notice it, we may not notice it. It's a little bit like we got here to a heavily polluting kind of climate change world little by little, right? We were sort of boiled like frog in water. I think all of that will change. I think by the middle of the century, I'm very, very confident that most fossil fuel use will go away.
People will have to find something else to complain about.
And there will be other big problems to solve, right? But I think that's one that we can absolutely solve. We can build a closed loop ecosystem, as I talked about with kind of the recycling piece. These batteries are going to require dramatically less inputs to make. We're going to all drive electric vehicles. We're probably going to fly on some electric planes, not for long distances, but for regional planes. Urban air mobility will become a reality.
The electric vertical takeoff and landing machines. I've been working on some of those. It's pretty fun stuff.
Yeah, they need better batteries, right? That's like the key limiter. But they're a lot more redundant than helicopters. They can be a lot safer. So I think we'll get around differently. We'll have abundant, cheap, clean energy. And when you have that, you can invest that in sort of solving whatever problem you want, right? If energy doesn't have this negative externality, I don't know what creative entrepreneurs are going to figure out to do with cheap, clean energy, but I bet the world will be a better place.
There's an interesting graph I saw that shows the price of energy kind of going down dramatically in terms of what's used by consumers until about the 70s, and then it kind of stalled and hasn't really gone down as much. It seems like it's similarly like the standard of living for the working class also didn't improve as much. And I don't think it's a full explanation, but it seems like at least correlated, where it's probably like really good for the working class and middle class to have even cheaper energy.
Right. I mean, it's such a fundamental part of our life, right? And so to like not be able to have that, the cost of that continue to go down, or at least what you get for what you pay not go up is kind of miserable.
It sort of drives everything. So we started this podcast to push back against a lot of the cynicism and pessimism across our country. And what would you say to the folks who believe the future is darker than the past and that we're heading into some kind of dystopian decline and none of this stuff's going to work?
Yeah, I just don't see it, right? I've been working on electric vehicles for my whole career, about 20 years now, and I think by the time I'm done with this, hopefully by the middle of the century or so, we will have gone from all fossil fuel transportation to all electric transportation, with save for a few jets. If that's not a brighter future, I really don't know what is. I know there's other entrepreneurs that are solving problems left and right in different fields, whether it's biotechnology or just a number of areas. So I know about my little piece. I don't believe that solving most of climate change is going to be a technology problem. I think we have the technologies. I'm watching them get invented. I'm watching them get scaled right now. There's lots of policy changes that need to happen, but I think fundamentally, once you give policymakers technologies that they can lean on, they inevitably come along, and I think we'll have a very, very clean energy future.
And just to summarize, like, why should we be optimistic about battery technology? Like what's happening right now? Like, why is it? How do we know this is actually advancing and working?
So if you go back to the beginning of Tesla, right? We basically, consumer electronics drove the birth of and the advancement of lithium-ion batteries to the point where you could build the first car with it. And then once we built the first car with it, now cars are actually driving the innovation for everything else. And so this shift in automotive is bringing so much capital and so many of the brightest minds to batteries. I mean, back when I got started, it is not the cool place to be, right? Like, all my peers were working on something else. I just found it fascinating. And now we're getting the best and brightest are coming to batteries, and it's really being pulled by the demand of cars. And as that demand grows, more and more capital, more and more talent comes to the space, and there's still tons of scientific opportunity, and so we are going to continue to crack different pieces based on the demand that we see.
What's if you graph over time, like over the last 30 years, is the percent of like improvement similar? Is it climbing? Like, is it like how would you measure that?
So it happens. There's not a particular Moore's law, if you will. It's much more generational shifts. So this graphite metal oxide chemistry went through an S-curve and totally flatlined. And that's sort of when I started to see it flatlining at Tesla as part of the impetus for starting Sila. Right. And so this next S curve that we're working on has the opportunity to kind of double it again from where it was. And so we're sort of at the beginning of the second S curve right now.
Awesome.
There's a couple kind of plots of that again in the white paper. Maybe we can flash it up for those watching on YouTube. And then the other interesting piece is the other plot I love is looking at battery costs against cumulative production, right? So you have this kind of learning curve, and every time you increase the amount of production by a factor of 2 or a factor of 10, it comes down a certain percentage. And so you can plot that out, and you can see the costs, if technology improves, trending to kind of $50 a kilowatt hour, which would have been unthinkable to people, just a few years ago. I mean, 100 seemed like a real stretch for everybody, and I think we're going to see 50 by the end of the decade.
And that's what actually gets to the scale where you could start using it for the grid and everything.
Exactly.
Else,
the grid is more of a cost problem. That's why it's so much smaller demand for batteries today. They're still just a little too expensive.
And once you have that, then we actually really can have solar and wind and nuclear solve all of our problems and store everything.
It will happen faster than people think.
Awesome. Well, that's a good note to end it on. Thanks so much, Gene.
Thanks, Joe.